Hi everyone, and welcome to The Sleepy Scientist. I'm really happy you're here. Tonight, we're going to go on a calm and quiet trip to learn something amazing. So get comfy, take a deep breath, and let's enjoy this peaceful science story together. Before we start, tell me in the comments, where are you watching from and what time is it for you right now? If you like relaxing science videos, don't forget to tap the like button. Now let's begin. In the beginning there was no blue, the earth, newborn and restless, wore a different skin, one of molten rock and fire. Its surface hissed with steam, cracked under the weight of a sky filled not with oxygen, but with gases that curled and boiled like breath from some ancient beast. Volcanoes ruled this place, their mouths glowing with liquid stone, and every moment was a tremble. Beneath this fiery crust, something miraculous began. Water, the kind that would one day cover most of the planet, seeped slowly from the deep. It did not arrive with a roar, but with a whisper, condensing from vapor, raining gently over centuries, collecting in hollows carved by heat and time. These early oceans were not like today's. They were greenish, acidic and heavy with minerals, reflecting not the sky but the memory of Earth's birth. And yet, in their chaotic shimmer, life found its first cradle. The sun, much fainter than the one we know now, poured soft gold across this primal landscape. Its warmth reached a world still unsure of its shape, where land masses drifted as phantom islands barely formed, constantly reshaped by tectonic fury. There were no trees, no grass, not even a single flower. Instead, the Earth's surface was bare, sculpted by wind and lava, kissed by tides that had only just begun to rise and fall. But below the surface, in the secret warmth of undersea vents, something stirred. Chemical reactions, fueled by heat and pressure, danced in the shadows of the deep. Molecules collided, bonded, and broke apart, rehearsing the steps of life's first choreography. No eyes watched it happen. No voice recorded the moment. But it was here, in these dark, mineral-rich waters, that biology began to hum its very first note. Imagine this ocean, thick with iron, kissed by sulfur, teeming with potential. It was not blue, but it was alive in its own way. Gases from the atmosphere dissolved into it, reacting with the metals below. Tiny structures, like microscopic cathedrals, formed around hydrothermal vents, shaping miniature worlds where life might hide. And somehow, within that warm and toxic brew, the building blocks of life assembled. Not in a single flash, but over slow eons, they came together, forming membranes, patterns and cycles. The first cells may have risen here, simple, silent and astonishing. They had no nuclei, no organelles, but they could grow, divide and survive, and in that they carried the future. The Earth, though young, was not quiet. Its crust shifted, broke and reformed endlessly. Continents as we know them did not exist. Instead, proto-continents, small scattered pieces of crust, floated on a mantle that churned like a boiling pot. These pieces bumped and collided, sank and re-emerged, forming temporary lands that would one day give rise to mountains and forests. The air above was thick with methane and ammonia, tinted orange and purple by the light of a dimmer sun and the glow of volcanic haze. To walk through such a world, if one could, would be to step through time itself, into a realm both alien and ancestral. Every rock told a story of fire, every ripple in the ocean whispered of possibility. Though the Archean eon lacked oxygen, it was not devoid of wonder. In the absence of breathable air, strange processes ruled the Earth's chemistry. The sky may have held lightning storms that danced for hours, crackling across the clouds like messages from the cosmos. These storms struck the land and sea, triggering more reactions, feeding the slow birth of life. In this chaos, the Earth was not just a planet, it was a poem unfolding in stone and water, heat and time. The oceans born in fire held the rhythm of creation, each wave a syllable in the language of becoming. They would one day turn blue, but for now they were still learning how to speak. Let's drift deeper into this ancient sea where daylight fades and warmth rises from beneath. Here in the quiet dark of the Archean ocean floor, the earth breathes differently, not through winds or forests, but through vents that open like mouths in the crust, exhaling heat and minerals into the surrounding water. Around these vents, the temperature shifts wildly, from near freezing to searing hot in seconds. Yet it is here that chemistry becomes choreography. Hydrogen sulfide, carbon dioxide, iron, and trace elements swirl and mingle, wrapping around newly formed molecules like dancers linking arms. This is not just chaos, it is creation disguised as chance. From these conditions, the earliest forms of life may have risen, not with a shout but a whisper, their structures simple yet profound, lipid membranes, strands of RNA, looping cycles of energy and replication. These were Earth's first experiments, and though most vanished, a few succeeded in surviving, multiplying and anchoring the great unfolding that would follow. Above these primal laboratories, the oceans themselves shifted in character. The Archean waters were thick with dissolved metals, and their colour likely resembled iron-rich green, like a tarnished mirror reflecting a sky choked with methane. Rain fell constantly, drawn from steam released by volcanic eruptions. This was not the gentle rain of a spring day, but a heavy sulfuric cascade that reshaped the surface with every drop. Rivers carved their way through newborn landscapes, transporting minerals into the sea. These rivers didn't feed forests or flowers. Those did not exist yet, but they fed chemistry, washing nutrients into cradles of creation, where primitive cells clung to rocks, absorbing what they could, multiplying slowly in the warmth. And still, the Earth changed. The planet's core, already generating a magnetic field, protected these fragile beginnings from cosmic radiation. It was a weak field then, not yet as strong as it would become, but enough to shield the surface from the worst of solar fury. In the sky, the moon, much closer than today, loomed enormous and bright, its gravity stirring powerful tides that churned the oceans. These tides were more than motion. They were mixers of life's ingredients, keeping the shallow seas dynamic and oxygen-poor but energy-rich. In these intertidal zones, where water moved in and out with rhythm, early life may have found its balance, protected from extremes, bathed in minerals, nudged by sunlight just strong enough to spark reactions, but not enough to burn. Life, still microscopic, began to leave traces. Stromatolites, layered structures built by colonies of cyanobacteria, formed slowly in warm shallows. They were the Earth's first great architects, trapping sediment, growing layer by layer, recording each day like a page in a diary. Their builders, though invisible to the naked eye, were rewriting the planet's destiny. These bacteria consumed carbon dioxide and, over eons, began to exhale oxygen as a waste product. At first, this oxygen reacted with iron in the ocean, creating vast deposits of banded iron formations, stone stripes that still tell the tale of this slow transformation. Only later, when the oceans could no longer hold the oxygen, would it spill into the atmosphere. But that moment was still far away. For now, the sky remained suffocating and strange. Back on land, tiny islands of protocontinents heaved and shifted. Some carried clusters of microbial life, tucked into cracks and tide pools. Others rose high enough to be kissed by rain and carved by wind. Though they bore no trees or grasses, these rocky outcrops hosted lichens and bacterial mats, life clinging to stone, absorbing energy, surviving. These were the Earth's earliest gardens, where biology learned to hold its ground against a world that had no room for softness. And through these scattered pockets, life endured. It learned to adapt, to share resources, to evolve, the Archean was a billion-year lesson in survival, trial, and silent perseverance. Even the air began to shift, ever so slightly. Trace amounts of oxygen, though not yet breathable, began to shape the atmosphere's chemistry. Lightning storms crackled across the skies, splitting molecules, creating new compounds. Ultraviolet light filtered through a haze of methane, triggering reactions that helped form complex organics. It was a messy, noisy alchemy, but it worked. And below all of it, the oceans kept breathing, their rhythms syncing with the moon's pull and the Earth's slow turning. Every wave that kissed the shore carried more than salt. It carried the memory of every storm, every drop of rain, every cell that dared to divide. This was not a peaceful world, yet there was beauty in its fire and foam. The Archean Earth, with all its violence and change, was tender in its own way. It was a place of beginnings, where life clung to the barest edges of possibility and turned them into permanence. What we see today, the continents, the oceans, the air we breathe, were all shaped by the quiet, persistent work of these ancient processes. They whispered across time, layering stirring sea, and planting the seeds of everything that would come. And though no eyes watched it unfold, the Earth itself remembers. Every mountain, every ocean floor, every fossil deep in the rock holds echoes of that time when the world was still finding its voice, and the oceans, born in fire, sang their first lullaby. Now imagine the Earth, slowly settling into its shape, not yet the blue marble we know, but no longer the violent ember it once was. The Archean Aeon moved with patience, stretching across nearly a third of Earth's history. In that span, oceans deepened, continents thickened, and the first languages of life grew more fluent. The cells that once clung to hydrothermal vents had spread, adapting to sunlight, to minerals, to heat and cold. Stromatolites now dotted the coastlines, building reefs of bacteria in the shallows. Layer by patient layer, they grew. Their lives were invisible, their labour silent, but they were sculpting a planet's breath. Every molecule of oxygen they released nudged the world closer to change, though that change would take millions of years more to be felt. For now, the air remained too thick, too strange. But the work of transformation was already underway. In the depths of the sea, other communities flourished in the dark. Some bacteria learned to thrive without sunlight, using sulfur or iron instead. These extremophiles, living in conditions no animal could survive, were shaping the chemistry of the world. Their byproducts changed the pH of the ocean. Their existence altered the crust where they lived. They were not simply surviving, they were engineering the future biosphere, without even knowing it. In the same waters, primitive genetic systems grew more complex. Mutations occurred, not with purpose, but with possibility. Some gave advantages: faster division, stronger membranes, better ways to harvest energy. Those lucky changes stayed, replicated, passed down. Evolution had begun, not as a drama, but as a slow tide, rising and falling across the eons. Above these oceans, the Earth's crust continued to dance. Protocontinents collided and merged, forming the early bones of what would become our modern continents. The mantle flowed beneath, creating hotspots of volcanic activity that both destroyed and created new land. The Earth's surface cooled, just enough to allow crustal fragments to stabilize. Tiny chains of island arcs formed, joining together over time. These lands were not stable. Earthquakes tore them, volcanoes shattered them, but they grew. Some began to form cratons, the ancient unmovable cores of continents that still exist today, their roots tracing back to the Archean. Walking on them now is like stepping across the skin of Earth's earliest dreams. The atmosphere too began to shift, not quickly, not visibly, but subtly. Oxygen, though still rare, was no longer instantly swallowed by iron and sulfur. Some of it began to linger, Slowly it filled pockets in the sky. Methane levels dropped. The sky changed colour, from the hazy oranges and purples of an anoxic world to something closer to blue. Light scattered differently now, and with that shift, the world's character transformed, temperatures adjusted, weather patterns evolved. The Earth, once dominated by extremes, now had rhythm. Winds moved across land, clouds formed and dissolved with greater nuance. The cycle of rain and evaporation became more consistent. These were the beginnings of a more stable climate, still raw, still unpredictable, but no longer purely violent. Within this fragile balance, life continued its quiet expansion. Genetic complexity increased. Some cells began forming internal compartments, small membranes within membranes, organizing their chemistry with greater precision. These were the ancestors of the eukaryotic cells, the blueprint for every plant, animal, and person to come. It would take another billion years for that complexity to fully blossom. But here in the Archean, the first whispers had begun. Microbes adapted to new environments, colonizing sediment, shorelines, and even the upper layers of the ocean. They formed ecosystems of competition and cooperation. They built communities where resources were shared and waste became food. This was not intelligence, but it was order. And in that order, the Earth began to resemble something that might one day host forests, oceans teeming with fish, skies full of birds. As the Archean eon drew to a close, its legacy was written not in monuments, but in memory. The rocks of that time, banded iron formations, green stone belts, ancient zircons, still tell its story. They carry within them the scars of collisions, the signatures of chemical transformations, the faint traces of ancient microbes. The continents that emerged during this time would become the scaffolding for all civilization. The oxygen that had begun to gather would one day ignite the Cambrian explosion. The life that evolved in darkness would one day walk under stars. And yet, in its time, the Archean was quiet, patient, and slow. It taught the Earth how to breathe, how to host life, how to hold itself steady across vast stretches of time. Today, when we look at the ocean, when we stand on granite cliffs, when we watch the wind stir the leaves, we are seeing the results of the Archean's gentle labour. Every mountain we climb, every breath we take, every tree that shades our path is part of a story that began in silence and stone. The oceans born in fire cooled into cradles. The skies that once choked life now sustain it. The continents that trembled found their footing. The Archean eon did not roar, it hummed. It whispered its changes through heat and pressure, through tide and chemical bond. And though no one was there to witness it, we are all its children. We carry its memory in every cell, every heartbeat, every echo of the deep. The story it told was not loud, but it was lasting. And if you listen closely, you can still hear it in the rhythm of the sea. The sky above the early Earth was not one we would recognize. It was thick, dark and foreign, a dome of gases that had never known the scent of a flower or the breath of a bird. There was no blue, no clouds drifting softly across a peaceful sky. Instead, a haze of methane and ammonia wrapped the planet like a veil. Sulphur drifted in plumes from volcanoes, and lightning cracked through the air in electric silence. These were not skies meant for life as we know it. They were skies forged in fire, woven from the breath of a planet still finding its form. Yet even in this heavy alien atmosphere, the seeds of something remarkable had begun to take root. The Archean sky was dense and low. Sunlight filtered through its layers in strange hues, copper, rust, and gold. At times, the light never reached the surface at all, swallowed by the thick mix of gases and dust. But this muted light was not useless. It warmed the oceans, it energized molecules, and it stirred winds that would shape landscapes long before life left the sea. Without oxygen, the air carried a different weight. It was not breathable, but it was alive with chemistry. Each gust carried particles from distant eruptions, droplets of acid rain, and gases released from the Earth's endless exhalation. This atmosphere, though toxic to us, was a canvas for creation. Deep within it, reactions unfolded constantly. Ultraviolet radiation from the sun, more intense than anything we feel today, struck the upper atmosphere and split molecules apart. This bombardment created radicals, highly reactive fragments of matter that triggered chains of chemical change. Ammonia turned into nitrogen. Methane reacted to form complex hydrocarbons. The sky was a laboratory stretched across the entire planet, and in that strange, sprawling lab, organic molecules began to form, not as life, but as the ingredients that life would one day require. They drifted through the air, settled into the oceans, and added to the slow recipe that brewed in Earth's warmth. There was no ozone layer then. The sun's radiation reached the surface more directly, burning the land and altering the chemistry of the shallow seas. But in this radiation lay power to crack bonds, power to create new possibilities. Along with the searing light came lightning, born of colliding gases and storm-laden skies. These electric storms danced across the early Earth for hours, maybe even days at a time. They flickered over the oceans, struck the volcanic islands, and ignited the sky with energy. In that flash of fire, simple molecules fused into more complex ones. In these sparks, life's early pathways found their beginning. The sky, wild and untamed, was not an enemy of life, it was a midwife. And what of breath in such a world? Not the breath we know, rich with oxygen and filtered through green leaves, but a different kind of exchange. The earliest organisms, anaerobic, ancient, breathed chemicals. They thrived in environments where sulfur, hydrogen and carbon dioxide filled the air and water. For them, oxygen was poison. They absorbed gases through their membranes and used them to power their tiny lives. In this way, the atmosphere and life were already intertwined, even if silently. The sky gave, and life took. Life exhaled, and the sky changed. Over eons, this relationship would shape both, slowly, invisibly, profoundly. At night, the stars looked different too. With less atmosphere to scatter their light, they burned more clearly, sharp, bright, unblinking. The moon, still drawing close circles around the planet, cast deep shadows across the landscape. Its gravity stirred tides that moved like breath across the land. These tides, influenced by the sky's rhythms, brought nutrients in and carried waste away. They helped shape coastlines, fed microbial mats, and churned the oceans. Even the sky's silence spoke. It measured time with its cycles, the rising and falling of the moon, the lengthening and shortening of shadows. These early clocks ticked softly above the growing Earth, unnoticed yet essential. As the Archean eon continued, some of the life below began to reach upward, not with limbs or lungs, but with chemistry. Cyanobacteria, early photosynthesizers, began to harness the light that filtered through the dense sky. They used sunlight to split water molecules, releasing oxygen as a byproduct. At first, the oxygen had nowhere to go. It reacted with iron in the oceans, sinking to the sea floor in layers of rust-coloured stone. But eventually some of it lingered. It drifted upward, molecule by molecule, into the waiting ski, and though the change was imperceptible at first, it marked the beginning of a slow transformation. The breath of the Earth was changing. The atmosphere that had once choked the surface with methane began to thin. The clouds shifted, the storms changed, and the first fragile hints of ozone formed far above. These changes brought new balances. Some gases faded, others increased, and slowly the light that reached the ground grew softer, clearer. In this clarity, life found new strength. With more usable light and less radiation, photosynthesis flourished. And as photosynthesis spread, so did the breath of a different world. A world with air, with sky, with the promise of blue. But that moment was still distant. For now, the Archean skies remained thick and strange, and every breath was still a chemical puzzle. And yet, within that puzzle, the Earth had already begun to learn how to breathe. Let's drift again beneath those heavy Archean skies into a world where the air was not meant for lungs, but for reactions. The breath of the planet was still young, its voice raw and filled with unshaped syllables of carbon and sulfur. This was a time when air was not yet a gift. It was a challenge, a riddle, wrapped in gas and flame, and yet the sky's breath was not empty. It was building something slowly, reshaping the Earth molecule by molecule. The balance of gases swayed with the rhythm of eruptions and tides. Methane bubbled from the seabed. Ammonia drifted upward from boiling springs. Carbon dioxide exhaled constantly from the crust, filling the atmosphere like a blanket, trapping warmth that the faint young sun could barely provide. The Earth, in its infancy, was wrapped in a greenhouse, its sky a furnace and its oceans kept liquid by the heat of its own exhalation. Without oxygen, the sky hosted other life-sustaining dances. Nitrogen, already abundant, began its quiet occupation of the atmosphere. It was inert, calm, not reactive, but it would become the scaffolding for amino acids, the breath of plants, the cushion of every inhale yet to come. In this era, nitrogen joined the other gases in silence, watching as Earth's chemistry unfolded. Then came the hydrocarbons, rising, falling, reacting in the air, drifting to the ground in rain that carried complex organics into the sea. This rain was not gentle, it came with acid and heat, laced with sulfur, biting at rock, carving gullies into the land, and feeding chemical reactions in every pool, every tide-washed bay. The very air was an alchemist's dream, stirring up new compounds with every gust, every storm, every flash of lightning through the cloud-heavy sky. The colours of this sky were a story in themselves. Without oxygen to scatter light, the blue we now take for granted had not yet been born. Instead, the heavens glowed amber at dusk, rusted red at noon, and burned violet during long storms. Sunlight filtered through haze thick with soot and volcanic ash, creating a world lit not by clarity, but by mood, dim, glowing, strange. The clouds were dark and high, boiling with heat from below, heavy with water that could fall at any moment. The skies were constantly active, never still, never quiet, and yet, in their unrest, they delivered the very ingredients of life. Through all their fury, they softened the earth, cooling its crust, seeding its seas, and whispering the language of future life into the soil. Below this roiling ceiling, the first great shift had begun. In shallows warmed by the sun and bathed in nutrient-rich waters, photosynthetic life bloomed. Cyanobacteria, ancient and small, had found a way to turn sunlight into energy. In doing so, they released a byproduct that the world had never truly known: oxygen. At first, this oxygen was consumed immediately. It reacted with dissolved iron in the oceans, settling to the bottom in thick layers of red and black stone, iron formations that would later build the skeletons of civilizations. For millions of years, this oxygen vanished as quickly as it appeared, caught in the great sponge of the sea. But slowly the saturation point was reached. The sponge filled, the iron ran low, and a thin, fragile layer of oxygen began to hover in the air. This was not yet breathable air. It was still a trace, still invisible to the kind of life we now understand, but it was enough to begin building something new. In the highest altitudes, some of that oxygen began to form ozone, a gas that would shield the Earth from ultraviolet light. This shield, delicate and incomplete, began to soften the sun's harshest rays. In response, photosynthetic life flourished further, deeper, wider. Tidal pools turned green, shallow seas shimmered with microbial mats, and the breath of the Earth shifted again. The air began to pulse with more than heat. It carried the signal of change, still toxic, still thick with methane, but no longer ruled entirely by it. The reign of oxygen had begun in whispers. Meanwhile, the atmosphere began influencing the surface in new ways. Weather patterns, driven by ocean heat and atmospheric gases, began to carve more predictable paths across the continents. Wind carried sediment, rain shaped valleys. The earliest signs of climate emerged, not as seasons we would recognise, but as patterns. Drier phases, wetter epochs, times when storms ruled and times when the skies grew strangely still. These rhythms affected microbial life, forced adaptation, fostered resilience. The sky was no longer just a blanket, it was a partner in evolution, shaping the world not by hand but by breath. In the pockets where oxygen gathered more densely, near dense colonies of cyanobacteria, microbial ecosystems evolved quickly. Some organisms began to develop resistance to oxygen's reactive nature. Others learned to use it, turning it into a tool for more efficient energy production. These were tiny revolutions, invisible in their moment, but profound in their consequence. The organisms that could adapt to this new breath thrived. Those that couldn't faded into extinction or deeper into the earth, where the atmosphere could not reach. Life and sky began to co-create each other. With every breath of these primitive microbes, the earth grew closer to the world we know. Still danger loomed. As oxygen accumulated, it began to threaten the very world that birthed it. Methane, a powerful greenhouse gas that had kept the planet warm, was broken down by oxygen, cooling the earth slowly. This would eventually lead to the planet's first ice age, long after the Archean ended. But in this moment, the balance still held. The skies darkened, lightened, and flared. Rain washed over the continents. The moon's pull churned the air and sea in tandem, and Earth's breath deepened, not as a rush, but as a slow exhale, pulling life up from water, inviting it to stretch toward light, and giving the sky its first gentle, invisible transformation. Now the sky had begun to shift, not with thunder or explosion, but with the slow unfolding of time. The gases that once ruled with fire and suffocation were giving way, molecule by molecule, to a new breath. Oxygen. It still lingered in thin layers, barely enough to touch the skin of the sea, barely enough to whisper change, but it was there, and with it came the promise of a different kind of Earth. Not the roaring planet of methane storms and volcanic skies, but something quieter, more hospitable. Yet the transition would not come without tension. The very thing that made life more powerful, oxygen, was also dangerous to the early forms that had built this world. Many of the first microbes who had survived by breathing sulfur and carbon now found themselves poisoned by the very air they had helped create. The atmosphere had changed, and the cost of creation was death for some and transformation for others. As more oxygen gathered in the air, the sky slowly began to lighten. It did not turn blue overnight. That colour, the one we now take for granted, was the result of light scattering through a sky filled with oxygen and nitrogen in just the right balance. In the Archean, it appeared first as a faded hue near the horizon, visible only in the rarest conditions, but it marked a threshold, a soft entrance into a new kind of atmosphere. Above the Earth, the ozone layer thickened, formed from oxygen molecules splitting and recombining under ultraviolet light. With this shield in place, fewer rays pierced the surface, allowing life to creep upward, closer to the sun. In shallow waters, microbial mats stretched outwards, basking in safer light, growing with new energy. The planet was learning not just to breathe, but to breathe with rhythm, with awareness. Below this changing sky, the Earth's surfaces responded. Rivers flowed more steadily, weather systems became more predictable, shaped by the new chemistry of the air. Rain no longer burned as strongly. Winds carried finer dust, feeding the oceans with nutrients. Clouds began to form more regularly, painting the sky with shapes never seen before. Each one told a quiet story of evaporation, condensation, release. The cycle of water grew more elegant, more balanced. In this dance between air and sea, life found opportunity. Some microbes evolved photosystems that worked better in the new light. Others formed protective shells to manage the oxidative stress. Still others began to collaborate, creating symbiotic relationships that would eventually lead to the rise of eukaryotic cells. Even the land felt the breath of the sky. On the proto-continents, those early islands of rock that floated like dreams across the mantle, the atmosphere's new chemistry began to shape soil. Organic material from dead microbes mixed with minerals forming the first hints of fertility. Lichens and microbial crusts clung to the rocks, breaking them down, releasing elements into the air and sea. The Earth's crust, once passive beneath the sky, became a participant in the planetary story. It absorbed gases, released others, and changed its shape in response. Volcanoes erupted differently now, their emissions shaped by the new pressures, new balances. Some belched carbon back into the atmosphere. Others gave rise to new minerals, oxidized by the breath of the world. And through all of this, the sky kept evolving. Slowly, as oxygen increased, methane dwindled. The powerful greenhouse blanket that had once kept the planet warm began to thin. This cooling would eventually usher in glaciation, but in the Archean's final moments, the balance still held. The Earth was neither too warm nor too cold. It was learning, adjusting, responding. Its breath, once chaotic, had found a pulse. Cyanobacteria continued to exhale oxygen, building up reserves in the oceans and sky. And with each exhale, the future drew closer. The future of animals, of plants, of civilizations. But even in this moment, with no forests, no eyes, no ears to witness it, the sky was already preparing to carry wings and voices. The silence of the Archean sky was deceptive. It was filled with the soundless roar of molecules colliding, of light splitting atoms, of invisible winds shaping continents. It held no birdsong, no thunder of hooves or rustle of leaves, but it was loud in its own way, loud with potential, loud with the weight of what it held. Every molecule of oxygen added to the air was a promise that the world could change, that life could grow, that breath itself could become a bridge between the sea and the stars. And that promise would echo through every era that followed. When the Archean eon finally gave way to the Proterozoic, the skies were no longer unrecognizable. They still lacked the full blue of today, but they carried the breath of life in full. Oxygen flowed in the air and the oceans. Ozone guarded the surface. And though life remained mostly microscopic, its chemistry had already rewritten the planet. The skies without air had become skies with purpose. Skies that could cradle birds, host clouds, hold storm, and reflect the dreams of those who would one day look up and wonder where it all began. And if they listened, they might hear it still. The ancient breath of a sky that once held no air, and yet taught the world how to breathe. In the earliest days of Earth's story, before forests whispered in the wind or rivers etched valleys through stone, the continents were only ideas, fragments adrift in a sea of fire and water. There were no grand land masses as we see them now, no sprawling mountains or familiar coastlines. Instead, there were shadows of continents, tiny rafts of crust that drifted atop the planet's molten mantle like broken leaves on a deep and boiling pond. These early fragments, called protocontinents, were shaped not by time's gentle hand, but by the violence of Earth's beginning, magma rising from beneath, cooling into rock, then shattering again. They were young and soft in the geological sense, their surfaces often thin, fractured and unstable. Yet within their folds something new was forming. In these fragile pieces of stone the planet was beginning to remember. The Archean Earth was a place of restless movement. Beneath the crust the mantle churned constantly, its heat rising in plumes that cracked the surface and spilled molten rock into the seas. Where these hotspots erupted, new land was born, briefly, violently, before being broken again by tectonic forces. These collisions, subductions and reformations were the Earth's way of drawing its first lines, etching the early map of what would become continents. But these outlines were blurry, tentative and constantly redrawn. The Earth's crust was thinner then, less rigid and easily reshaped. The rocks that formed were different too, greenstones rich in iron and magnesium, ancient tonalites and gneisses that would one day become the stable heart of continents. These were the first storytellers, their minerals recording every burst of heat, every moment of stillness, every encounter between land and sea. Imagine walking on such a landscape, a barren, windswept, shaped by fire and steam. The ground would not feel familiar underfoot. There would be no soil, only naked rock, pitted by acidic rain and cracked by heat. Pools of water might steam in shallow basins, their edges lined with colourful microbial mats. Geysers would hiss and roar, pushing minerals into the air. The silence would be interrupted only by the distant rumble of a volcano or the soft splash of water against jagged shores. Yet in this harsh terrain, life had begun to settle in. Microbes clung to the stone, forming colonies in sheltered crevices, building biofilms that slowly, over time, would help weather the rock. Even in stillness, the stone was changing. It was being shaped not only by pressure and heat, but by life, tiny, persistent, and patient. These early land masses, though small, were powerful in their influence. They disrupted ocean currents, created shallow lagoons, and offered refuge for the sun-loving cyanobacteria that painted the edges of the sea green. As they grew larger and more numerous, they altered the planet's balance, affecting how heat was distributed, how rain fell, how tides moved. Protocontinents also began to merge, slowly colliding under tectonic pressure to form larger bodies of land. These collisions generated mountain-like ridges, sparked new volcanic chains, and buried some of the earliest crust deep into the earth, where it was transformed by heat and pressure. And in that transformation, the continents found their voice. The minerals realigned, the crystals grew, and the rock began to tell a story, one of birth, of change, of endurance. The earliest granite, a rock we often think of as old and immovable, began to appear in this time. It was a new kind of stone, lighter, more buoyant, able to rise above the denser basaltic crust that covered most of the earth. With its emergence came the foundation for stability. These granitic cratons formed the unshakable roots of continents, so deep and solid that they still form the cores of our continents today. Within them lie the oldest minerals on Earth, zircons more than 4 billion years old, each one a time capsule of heat and memory. They speak of ancient oceans, of rains long vanished, of a sky before breath. They whisper from within the stone of a time when Earth was young, and the continents were only beginning to learn how to stand still. Over millions of years, erosion began to shape these early lands. Rainfall carved channels through the rock, wind blasted it into sand. Rivers, driven by tides and storms, wore down mountains into plains. Sediment settled into layers, compressing into new stone that would carry traces of microbial life, volcanic ash and mineral flows. These layers built stories in quiet accumulation, waiting to be lifted again by the next tectonic push. The continents were not yet stable, but they were becoming more than shadows. They were becoming memory, living memory etched into stone. Every crack, every vein of quartz, every folded layer of metamorphic rock held the echo of the Archean's fire and water, of the forces that pressed Earth into form. And while they held memory, they also gave shelter. Along their coasts, shallow seas grew rich with life. Stromatolites flourished in sunlit waters, building towers of mineral and microbial slime that reached toward the sky. These living rocks, shaped by the breath of cyanobacteria, grew only where the sea was quiet and shallow, conditions made possible by the rise of stable land. The continents offered anchor points for tides, boundaries for ocean currents, and homes for evolving ecosystems. Without them, life would have remained adrift, scattered in the depths. But with them, life began to localize, to diversify, to leave fossils in the rock. In this way, stone and life became partners. The continents, once shadows, were now beacons. And beneath their surfaces, the story of Earth's becoming was still being written, one silent layer at a time. Let's return to those first fragments of land, the ancient protocontinents that floated like thoughts above the restless mantle. They were not grand yet, not the towering continents we know today, but they were steadying, hardening, learning to endure. Beneath their surfaces, a silent struggle unfolded. Heat from the Earth's core pushed upward, pressuring the rock, folding it, transforming it. Each collision of crust with crust gave birth to mountains that rose not with sudden violence, but with the slow grace of geologic time. The roots of these mountains plunged deep, anchoring the crust against the flow of the mantle. These roots, rich in minerals, cooled slowly, crystallizing into strong ancient rock. They became the cratons, the indestructible bones of the continents. And while the surface above eroded, washed by rains and battered by winds, these cores held steady, unmoved across billions of years. In the Archean, land was never still for long. The surface plates, thinner and hotter than today's, moved with more vigour, more fluidity. They jostled and broke like drifting ice flows on a warming sea. Where they met, great subduction zones opened, swallowing oceanic crust back into the deep. And in these zones, new mountains were formed. Volcanic arcs rose from the sea, their summits steaming and unstable, but always adding to the patchwork of land. Lava poured across old rock, ash darkened the skies, and yet after each eruption the land was reborn. Thicker, stronger, more resilient. The whisper of stone was beginning to take shape, not through peace but through persistence. Above ground, the surface of these protocontinents began to evolve. As volcanic activity slowed in some places, more stable environments formed. Water pooled in basins, creating lakes and inland seas where sediment could settle undisturbed. Wind began to sort grains of sand, depositing them in rhythmic layers. Rivers, guided by the contours of new hills, carved out valleys, and the rain, still acidic but softening, wore down the once sharp ridges. In these lowlands, life began to creep in greater numbers. Mats of cyanobacteria spread across the rocks, binding dust, capturing light, and exhaling oxygen. The stone, once cold and inert, now hosted life that altered its very surface. The continents were becoming more than foundations, they were laboratories for evolution. Deep within the crust, the pressure of time created metamorphic rock, stone born not from fire or sediment, but from transformation. Shale became slate. Basalt turned to amphibolite. Minerals realigned, creating bands of colour and strength, each telling a story of buried heat and ancient collision. These rocks, now uplifted by tectonic forces, revealed cross-sections of Earth's memory. In their folds and veins, geologists today read the temperature of the early Earth, the presence of water, the timing of collisions. The land itself had become a record keeper, its pages written in minerals and melted stone. And as the continents continued to grow, so did their impact on the planet's systems. They disrupted wind patterns, deflected ocean currents, and introduced new cycles of erosion and deposition. The weathering of continental rocks drew carbon dioxide from the atmosphere, slowly reducing the greenhouse effect. This cooling feedback, gradual but relentless, began to lower global temperatures. Though the Archean remained a warm era overall, hints of the Earth's cooling trend had already begun. In the long rhythm of the planet's breath, this was the faintest exhale before the chill of the Proterozoic to come. Still, life clung to the land. In the warmth of tidal flats and shallow seas, stromatolites grew taller. They fossilized the passage of time in layer after layer, year after silent year. Some became islands unto themselves, rising just above the tide to catch the morning sun. Others stretched across entire coastlines, like microbial reefs anchoring the edge of the world. These structures were not just homes for bacteria, they were engines of change. By photosynthesizing, they continued to release oxygen into the oceans and atmosphere. And as oxygen rose, it interacted with the stone. Iron oxidized into rust-red bands. Sulfur reacted into new minerals. The land and life were now locked in partnership, their chemistry forever intertwined. Every continent, even in its infancy, bore the marks of time. Fault lines crisscrossed the terrain. Folds in the rock recorded the direction of ancient pressures. Layers of ash told stories of eruptions lost to memory. These features, still visible in some of the Earth's oldest rocks, are not just scars, they are inscriptions. They are the Earth's own poetry written in granite and schist, sung in the language of pressure and flow. And while these continents lacked trees, rivers teeming with fish, or soil thick with roots, they contained within them the potential for all those things. They were stage and story both, silent, patient, waiting. The wind that moved across these young lands carried more than dust. It carried spores, gases, echoes. It brushed the surface of the rocks that would one day form the heart of every continent. It carved edges into cliffs, piled sand into ridges, and whispered across the microbial mats that painted the earth in green and gold. These whispers, carried through time, left their mark on the land. Over millions of years, these winds would grow more complex, shaped by mountain ranges, redirected by valleys. But here, in the Archean, they still spoke a simpler tongue, one that touched only stone and sea and sky. And so the continents, once mere shadows on the sea, grew bolder. They rose, fell, collided, and reassembled. Each cycle made them stronger, more stable. Each eruption added weight to their foundations. And with every movement of stone, the earth wrote itself into being. The whisper of stone was now a hum, steady, deep, and filled with memory. It would echo through time, through ice ages and forests, through deserts and cities. And even now, if you place your hand on ancient rock, you can feel it, the slow, breathing pulse of a world that learned to endure. Let's listen now to the quiet language of time, the voice that speaks not in words but in pressure, in temperature, in stone. By the close of the Archean eon, the continents had grown, not in sudden leaps, but in slow accumulation, grain by grain, eruption by eruption. What began as scattered volcanic arcs and drifting microplates had gathered into larger landmasses, anchored by thick roots of buoyant granite. These ancient cratons, shielded from subduction and insulated by their depth, became the first truly stable places on Earth. They no longer drifted with reckless speed. They no longer vanished beneath the waves. They stood firm, their roots reaching hundreds of kilometers down, their surfaces weathered but resilient. Around them, younger rock accreted, volcanic layers, sedimentary blankets, metamorphic skins, all fusing into the beginnings of continental cores that still persist beneath our feet today. The story of stone is not told in moments, but in layering. The surface of the earth became a canvas for deposition. Ash from distant eruptions, silt from muddy deltas, particles carried by wind and washed by rain. Rivers etched deeper into these rising continents, carving out ancient basins that filled with water and sediment. With time, these sediments hardened into sandstone, shale, and limestone. Pages of Earth's early diary, each layer a record of conditions long lost. Some of these rocks would later be buried and baked into metamorphic complexity. Others would remain near the surface, waiting for human hands to read their stories. But all of them bore the mark of time, of pressure, of Earth's early attempts at structure. In this final phase of the Archean, the atmosphere had changed just enough to allow for broader transformation. Oxygen, though still a minor component, had begun to gather in the shallows, creeping into the air with each breath of the microbial mats that painted the coastal edges of the land. The impact of this oxygen was slow but profound. It reacted with exposed rocks, rusting iron, creating colourful mineral bands in cliffs and outcrops. These banded iron formations were both beautiful and brutal, signs of oxygen's rise, but also graveyards for countless anaerobic microbes who could not tolerate the change. The breath of the continents was becoming cleaner, but also more dangerous. This oxygenation would set the stage for everything that came next, including the emergence of complex life. But first, it would bring a quiet reckoning to the world it was transforming. Above the land, the sky had softened. Once thick with methane and carbon, it now held the faintest whispers of blue. The ozone layer, forming high in the atmosphere from oxygen's interaction with sunlight, began to protect the surface from ultraviolet radiation. This allowed life to grow closer to the light, to expand into shallower waters, and even to survive at the very edge of land. On the continents themselves, microbial colonies began to venture further inland, colonizing damp crevices, steaming geothermal pools, and moist volcanic soil. These were the Earth's first terrestrial settlers, not plants or fungi, but bacterial mats, inching forward in slow waves, changing the land with each new layer they spread. Over time, the interplay between these colonies and the rock beneath them would begin to create soil, the thin, vital skin of life that blankets the continents today. The earliest soils were rudimentary, formed from weathered rock and organic waste, but they were enough to hold moisture, enough to support thicker microbial growth, enough to further break down stone into sand and silt. The continents were not just lifeless platforms anymore, they were becoming ecosystems. They were beginning to host the ingredients of future forests, of rivers full of fish, of animals walking on land. And though none of these had arrived yet, the blueprint was settling in place quietly in the chemistry of rock and air. The land too began to move with new rhythm. Plate tectonics, once chaotic and fluid, became more organized. Subduction zones deepened. Mid-ocean ridges lengthened. Continental collisions built up mountain belts that rose higher than anything before. These changes reshaped the face of the Earth. Highlands emerged that altered weather patterns. New basins opened that changed the flow of the oceans, and through these geographic transformations, life followed. Shallow seas lapped against ancient cliffs. Warm tidal zones hosted fields of stromatolites. Coastal shelves, rich with sunlight and nutrients, became oases of photosynthetic activity. The continents shaped life, and life in turn shaped the continents, etching its breath into every stone, every layer, every breeze. And so the Archean eon approached its close, not with finality, but with a deepening sense of what was possible. The Earth had grown quieter, cooler, more complex. Its crust had thickened, its air had shifted, its oceans had changed colour, and across its land the fingerprints of life had begun to leave lasting impressions. The stone, once molten and aimless, now held meaning. It was no longer just material, it was memory. It told the story of fire, of impact, of silence and sound. It whispered of the long unfolding of continents, the weight of water, the breath of gas, the birth of form. Today, when we walk upon the land, when we rest on ancient bedrock or study the grains of a weathered cliff, we are touching the bones of that distant world. The stone beneath our cities, our mountains, our quiet forests carries the record of a time before time when the earth was still learning how to hold itself together. These whispers of stone do not fade. They echo still in every quaking fault, in every folded mountain chain, in every fragment of granite that holds the chill of deep time. And if we pause, if we listen carefully, we may hear it too, the quiet, enduring voice of the continents, formed in fire, steadied by time, and forever singing their slow song of memory. Long before forests reached toward the sun, before animals stirred in the sea, and before green flooded the surface of Earth, there was life. Not the kind that swam or walked or flew, but a more patient, more enduring kind. This life existed in darkness, not because the sun had failed to rise, but because the light had not yet become useful. The earliest organisms did not seek the sky, they clung instead to warmth in the deep, to chemicals rising from beneath the seafloor, to the secret engines of a young and volatile Earth. They lived in a world without oxygen, without eyes, without seasons, and yet they were builders, microbial architects that shaped the Earth in silence, in stillness, and in scale too small for the human eye, yet vast enough to change the course of the planet's destiny. Beneath the ancient seas of the Archean, cracks in the Earth's crust opened to the churning interior. These were hydrothermal vents, black smokers and white chimneys, spewing mineral-rich water into the ocean. Around them, the conditions were harsh. High pressure, extreme heat, and toxic chemicals like hydrogen sulfide and methane. And yet, in these cauldrons of extremity, life took root. Microorganisms, known as chemolith autotrophs, used the chemicals pouring from these vents as fuel. Without sunlight, they harvested energy from the Earth's own breath. They were ancient chemists, assembling life's first pathways not from light, but from rock, water and fire. These were the first architects, and they built not with stone or wood, but with molecules. Their communities formed dense colonies clinging to mineral spires, creating ecosystems where none should exist. Some grew in filaments, others in mats. They exchanged gases, shared nutrients, and evolved methods to survive the extreme gradients of heat and pH. And in doing so, they laid the foundations of Earth's biosphere. These microbes did not just survive, they transformed. They altered their environments, creating niches for other organisms, cycling elements like sulfur and nitrogen long before any plant or animal walked the Earth. Their metabolic byproducts began to fill the ocean with new compounds, feeding a slow chemical transformation that would echo upward into the atmosphere. They were the unseen gardeners of a planet still waiting to bloom. In the shallower waters closer to the surface, different microbial architects emerged. Cyanobacteria, capable of photosynthesis, began to harness sunlight to split water molecules, releasing oxygen as a waste product. But this oxygen had nowhere to go. It reacted instantly with iron dissolved in the ocean, forming rust-coloured minerals that fell to the seafloor. These banded iron formations still line cliffs and ridges today, striping the world in red and black, a mineral memory of Earth's slow breath. The oxygen produced was invisible to the eye and irrelevant to the earliest microbes. But over millions of years, it changed everything. These cyanobacteria, floating in quiet mats or building layered structures called stromatolites, were not only capturing energy, they were altering the very atmosphere of the planet. Even in the deepest darkness, other microbial communities thrived. Some lived within the rocks themselves, kilometers beneath the surface where heat and pressure were nearly unimaginable. Others inhabited the pores of sediment, sealed off from light and air. These were Earth's quietest life forms, yet they may represent the most ancient and enduring lineage. Their metabolism was slow, their reproduction glacial, but their presence was constant. And together, they created a deep biosphere, a hidden world beneath the crust, where life could endure even the planet's most violent episodes. Meteor impacts, volcanic winters, ice ages, none of these could touch the life that hid in stone. This resilience would shape the story of life on Earth forever. Across the globe, microbial mats spread like quilts across the shallow seafloor. They captured sediment, bound grains of sand, and over time built up layered structures that fossilized into stone. These stromatolites became Earth's first great cities, living, growing monuments to the patience of life. They were not just passive structures, they were active ecosystems, with inner layers adapted to light, darkness, and chemical gradients. Each layer had its own community, working in cycles of oxygen production, carbon fixation, and nutrient recycling. These mats formed reefs that changed the flow of water, that trapped organic matter, that created new habitats. They were engineers of space and time, altering their world with each slow layer of growth. In the absence of predators, these microbial ecosystems thrived, but they also competed. They developed defenses, strategies, and cooperative behaviors. Some microbes excreted protective substances that created barriers. Others exchanged genetic material, adapting faster to environmental shifts. Horizontal gene transfer, where DNA was passed directly between cells, became a key evolutionary tool, allowing new traits to spread without waiting for generations to pass. This networked evolution gave rise to diversity, resilience, and eventually to more complex forms, and all of it was happening in silence, before the first multicellular life had even formed. These microbial architects also played a crucial role in Earth's geochemistry. They mediated the carbon cycle, pulling carbon dioxide from the atmosphere and locking it in organic molecules. When they died, their bodies sank to the ocean floor, trapping carbon in sediments that would later become rock. This slow burial helped regulate global temperatures, balancing the greenhouse effect and allowing Earth's climate to stabilize. It was not a perfect balance. Volcanic eruptions still pumped gases into the air, but it was enough to maintain the conditions life needed to continue. The microbes were not just passengers on the planet, they were its stewards, shaping its chemistry, its temperature, and its future. By the end of this earliest age, the Earth had already become a living planet, not because of forest or rivers or animals, but because of these microbial pioneers. They transformed the oceans, they altered the atmosphere. They wrote the first chapters of Earth's biological history not in ink, but in chemical bonds, in fossils too small to see, in changes too slow to feel. They were life before light, creatures of the deep, the dark, the unseen. And though their names have been lost to time, their work remains. It is etched into the stone, dissolved into the water, breathed into the sky. It is the foundation on which every green leaf and beating heart now rests. It is the architecture of a world that learned to live before it learned to see. Let's drift deeper now into the thick, silent oceans of the Archean Earth, where the sun barely reached and the only light came from the glow of hydrothermal vents. Here, in the deep calm beyond the tides, life moved without eyes, without nerves, without any thought of tomorrow. These were ancient cells, still learning how to be alive, and yet they worked in harmony with their surroundings. They followed gradients of heat and chemistry, like a tide following the pull of the moon. They floated, clung, divided. Their membranes held just tightly enough to keep their fragile interior from spilling into the sea. Inside them, reactions sparked, glucose forming from carbon, ATP cycling through tiny engines, proteins folding like flowers in a hidden field. It was quiet work, the kind that built everything. No applause, no recognition, only the slow unfolding of complexity. In the warm shallows closer to land, microbial mats spread wider, thicker. They formed carpets across ancient coastlines, where waves could still reach but rarely disturbed. These mats were multi-layered worlds unto themselves. The top layers absorbed sunlight, performing photosynthesis with the help of pigments tuned to the filtered light. Deeper layers carried out other processes: fermentation, nitrogen fixation, sulfur reduction. The mat was a microcosm of the future biosphere, complete with energy transfer, waste recycling, and niche specialization. Some microbes fed directly on the light, others fed on the byproducts of those above. A few burrowed downward, seeking the warmth of the stone below. They needed no eyes to know their place. Chemistry was their compass, and together they built a stable, thriving structure, alive but unmoving, enduring but ever-changing. The success of these mats altered the Earth profoundly. They stabilized sediments, preventing erosion. They changed the reflectivity of coastlines, subtly affecting local climate. They trapped gases and transformed them, exhaling oxygen that drifted slowly into the water above. That oxygen, though still quickly absorbed by dissolved iron, left faint traces in the form of rust-coloured minerals that settled into long, thin bands of stone. These banded iron formations layered the ocean floors with red memories of invisible breath. Each band marked a moment when oxygen briefly outpaced iron, a soft sign of life winning a little more ground. Over millions of years, the bands thickened, becoming permanent features of the Earth's crust. They were not just rocks, they were signatures, left behind by microbes who never knew they were changing the world. In the depths, other strategies emerged. Methanogens, ancient and mysterious, began producing methane as a waste product of their energy cycles. This methane rose into the atmosphere, thickening it, warming it, preserving the planet's heat under a fainter sun. Without it, the Earth might have frozen. With it, the climate stabilized. These microbial emissions, invisible and odorless, were climate control mechanisms born billions of years before humans. Their contribution to the greenhouse effect kept the oceans from turning to ice and allowed life to expand outward. Every breath of methane was a message. The world is still warm. Life can continue. These microbes, often buried deep in anoxic sediments, held the planet's warmth in their tiny hands. Some microbes formed partnerships that would one day redefine biology. In rare moments, a larger cell engulfed a smaller one, not to consume it, but to keep it. Over time, the engulfed cell stopped living independently and began to function as part of its host. This was the beginning of endosymbiosis, a silent revolution that would give rise to mitochondria and chloroplasts, organelles that power every complex cell on Earth today. The first of these unions were fragile, experimental, many failed, but a few endured, and their descendants live in every animal, plant and human. These early mergers were not plans or goals, they were chance events, made permanent by utility. They were the seeds of complexity, planted by microbes who had no idea they were inventing the future. Meanwhile, genetic material became more fluid. In the close quarters of microbial mats and sediment layers, genes passed laterally between cells, creating networks of information rather than family trees. This horizontal gene transfer accelerated adaptation, allowing entire populations to evolve together. One beneficial gene could spread not in generations, but in hours. These exchanges blurred the lines between species, making the early tree of life more of a web, interwoven, dynamic and shared. Life was no longer isolated experiments in distant corners of the sea. It had become a global collaboration, carried on currents stirred by tides linked by DNA. The ocean itself began to change in response. As microbial life expanded, so did the range of dissolved compounds in the water. Nitrate, phosphate, ammonia, sulfate, all were cycled and recycled, balanced by metabolic processes. These cycles grew more stable, more efficient, more intertwined. The biosphere was now an engine, driven by light, fed by chemicals, cooled by methane, and exhaling oxygen. It was a quiet machine, one that ran not on gears, but on gradients. And it never stopped. Every day, microbes carried out their ancient tasks, dividing, converting, responding. They had no thoughts, but they had purpose. Their purpose was life itself. Above them, the skies held more oxygen with each passing epoch. Still toxic to most early microbes, this gas slowly rewrote the chemistry of the surface world. Iron fell out of the ocean in layers. Sulfur cycles shifted. Carbon dioxide was pulled from the air and stored in rock and biomass. Bit by bit, the Earth's environment tilted towards something new. These changes were slow, often invisible but unstoppable. The air changed, the sea changed, and so did the microbes. Some adapted to oxygen, others fled to anoxic environments, still others disappeared. But none of it stopped the momentum. Life was no longer just surviving, it was transforming. And beneath all this, the Earth continued to breathe. Its mantle still churned, its volcanoes still roared. But now, those outbursts were not alone. They were answered by the breath of microbes, by the sigh of stromatolites, by the chemical rhythms of cells that had learned to endure. Life before light had built the scaffolding. The Earth was ready for more, and though it would take another billion years for complex organisms to rise, everything they needed had already been made. In darkness, in silence, in the soft and tireless hands of the microbial architects who shaped the very first version of home. Now we reach the final chorus of the microbial age, when the quiet architects had already written the first verses of Earth's living song. By the end of the Archean, life still had no eyes, no limbs, no voice, but it had shape, depth, and purpose. In the dark folds of the ocean floor, and in the calm shallows of sunlit shores, microbial life thrived not as isolated pockets, but as an interconnected web. Each species played its role in a complex system of exchange, a system where carbon, nitrogen, sulfur, and oxygen passed from one cell to another in an endless rhythm of transformation. These were the Earth's original engineers, not merely survivors, but creators of stability, chemistry, and change. And though they never saw the sky or heard the wind, they made both possible, preparing the world for the life that would one day name it. By now, oxygen had quietly gathered in the seas and begun its slow migration upward. The once iron-rich oceans turned clearer as the metal settled into the deep in layers of red stone, each layer a sentence and each stratum a breath. The ocean no longer looked as it once had. The colours had shifted. The chemistry was different. The very surface tension of the water, the way it held itself together, had been changed by the substances life had released into it. And the sky, once thick with methane and haze, began to reveal a new softness. The earliest trace of blue began to stretch over the horizon, diluted by volcanic gases, but still present, a sign that the air had begun to scatter sunlight in a new way. This transformation did not happen in days or centuries. It took millions of years, built molecule by molecule, breath by breath. At the heart of this change was the microbial world, still small, still unseen, but more organised than ever before. Mats grew more diverse, layered not just by function, but by environmental sensitivity. Some microbes could tolerate more oxygen, while others lived only in the depths of the mats where it never reached. Microbial colonies began to specialise more distinctly. Filaments extended to capture light. Slimes thickened to protect against UV. Genetic material passed back and forth like a shared memory. And through this slow but constant exchange, new innovations emerged. Better enzymes, tighter membranes, improved photosynthetic systems. All of it silent, all of it invisible, and all of it essential. Some microbes began to leave their marks in stone, not just indirectly, but as fossils. Tiny impressions in ancient sediment reveal the shapes of filamentous organisms preserved by chance in the fine muds of Archean lagoons. These marks were not drawings or writings, but signatures nonetheless, evidence that life had found a way to leave something behind. As the mats thickened and spread, they built new kinds of sedimentary structures, not just stromatolites, but other microbialites layered and branching in forms that defied the logic of non-living geology. These structures became habitats themselves, creating oxygen-rich zones for future organisms to inhabit. They were self-built environments, proof that even without hands, life could shape its own world. Beneath the surface, the deep biosphere remained alive and well. Even as surface oxygen levels climbed and shallow waters became more oxidized, the subsurface microbes continued to thrive in anoxic pockets. They digested rock, metabolized metals, and produced gases that helped regulate the planet's atmosphere from below. These deep microbes, cut off from sunlight for billions of years, may have formed a stabilizing force, buffering Earth against extremes, recycling elements too heavy to float, and anchoring the biological systems that flourished above. They were the custodians of Earth's interior, and their legacy endures to this day in rock samples drawn from kilometers below the surface where microbial DNA still clings to mineral grains like ancient whispers. And then, in a slow crescendo, the oxygen produced by surface life began to overflow its chemical sinks. The oceans could no longer absorb all of it. The iron had been oxidized, the volcanic gases had been neutralized, and so oxygen, no longer captured by the sea or the crust, began to gather in the atmosphere. It happened slowly, millions of years accumulating molecules barely perceptible by any measure. But as it built, everything changed. The composition of the atmosphere shifted. The greenhouse gases that had kept the Earth warm began to wane. Methane, highly sensitive to oxygen, was broken down, reducing its warming effect. The Earth cooled. Ice crept across continents. The first known glaciations began, driven not by celestial mechanics, but by the breath of microbes. It was the first time life had changed the climate on a global scale. Some ecosystems collapsed. Microbes that could not tolerate oxygen retreated underground or into isolated niches. Others adapted, evolving defences, antioxidants, and respiration pathways that turned oxygen from a toxin into a tool. These were the ancestors of everything aerobic from moss to mammal. They were not yet complex, but they held the toolkit for complexity. Mitochondria, descended from once independent bacteria, became permanent fixtures in the cells of these new survivors, making energy more efficiently, supporting more complicated structures. Life had entered a new phase, and the microbial world was its midwife. The great leap into complexity would come in the eons ahead, but its roots were planted here, in the cooperative, resilient, endlessly adaptive world of the Archean microbe. And so, as the Archean eon came to a close, it left behind no monuments of bone, no cities of stone, no voices echoing through the air. But it left something more permanent, the breath of life in the sky, the memory of microbes in the rock, and the promise of evolution in every strand of DNA. The microbial architects, who had lived in the dark, who had worked in silence, who had never seen a sunrise, had changed the earth forever. They built not with hands, but with time, not with tools, but with chemistry. And their work is still visible, in the oxygen we breathe, in the rust-red hills that mark ancient seas, in the genes that shape every cell of our bodies. To this day their descendants endure. In the hot springs, in the deep crust, in the oxygen-free lakes and salt pans, the oldest life on Earth still lives as it once did. Quiet, small and tireless, they do not ask for light. They do not ask for space. They only continue breathing the breath they helped create, whispering to the stone and remembering the time when the Earth was young and life had not yet learned to see. They are the living memory of the world before light, the first dreamers, the first builders, the silent ancestors of everything to come.